Hello, in this section we're gonna go over functions. To start with function, we know that there are three parts, as you've seen in college algebra or pre-calc courses. So there is the domain. Well, you've seen in the past is the range, but I'm gonna tell you the difference between the range and codomain. But here we talk about domain, codomain, and that function that takes element from the domain to the codomain or range. So, for example, if the domain is set of maybe integers such as 0, 1, 2, 3, 4. So in this domain you have this element 0, 1, 2, 3, 4. So the function that takes elements from the domain to the codomain will be f of s, which is s plus 3. 0 plus 3, you get 3, maybe 4, 5, 6, and 7. So this is basically, right here is the range, which is, so the codomain is a set of values that possibly be output, while the range is the set of values that actually are output. So 3, 4, 5, 6, 7 is the range. Well, codomain can have many other values here. Let's see some more examples. So here f is a function from s to t, and here is how we write it, f and dot s to t as the domain, and t is codomain. The association itself is a set of ordered pair, each of the form st. For example, we have in this example here 0, 3. That's an ordered pair, or 1, 4, and so on. And 2, 5, where s belongs to the domain s and t belongs to the codomain, and t is the value from t that function associates with the value s. So t will be f of s, as we've seen in this example. So here is the definition, and with some terminology for functions. So the function is a mapping from f. So the function is mapping from s to t, and s is domain f, t codomain, and also t can be the image and s is the pre-image. And so in here I have a function f that takes integers to an integer. So domain is set of all integers, and codomain is set of all integers. Be defined by f of x is x squared. So you take, so in this example it says where is the image of negative 4. So if I have a minus 4, I square it, where we get 16. So the image of negative 4 is 16. So where would be the pre-image of 9? So where is the number? If I square it, I get 9. So it's 3 and minus 3. Both of them, if I square them, you get 9. So the pre-image of 9 is 3 and minus 3. A function from s to t is a subset of s, t. So this is the Cartesian product. By definition of a function, a binary relation that is a 1 to many or many to many cannot be a function. So definition of function, for every x there is one and only one y. And that's why in pre-calc a circle is not a function, because one element x from the domain gonna give me two elements in the range. So this is not a function. So for every x there is one and only one y. So if this is your pre-image and this is your image, so the function f, to be a function you cannot have for example, when x has two y's, y1 and y2, this is not a function. So leaving from here to the image set, you cannot have these two arrows leaving from one x, and that's hence the definition. So for every x there is one and only one y. And we did in pre-calc the vertical line test. If it crosses the graph into point, that means one x will have two y's, which is not a function. So all what I draw here, this is not a function. So let's see this example here. What we have is g from r to r, where g of x is x to the third. Is g a function? So here we take every element from the domain, which is the set of all integers, and then you're gonna cube them, you're gonna get a real number. So basically you get another set of integers, which is a subset of real numbers. So the codomain is, so for every x in z there exists one and only one y corresponding to f of x equal x to the third. Thus this is a function. So are this g and f the same function? Now the question, are they the same? I would say they are not, because the domain is different. Here we have r and here we have z, which change the set of order pairs. For example, here I could have radical 2, but I wouldn't have this order pair in f on this, because the radical 2 is not an integer, it's a real number. And therefore we're going to get into what is equal functions. Two functions are equal if they have the same domain, the same codomain, and the same association of values of the codomain with values of domain. To show that two functions with the same domain and the same codomain are equal, one must show that the association are the same. This can be done by showing that given an arbitrary element of the domain, both functions produce the same associated value of that element. That is, they map it to the same place. So they map to the same place. So let's see this example here. So what we have is this. S is 1, 2, 3, and T is 1, 4, 9. And the function f that takes S to T is defined by f will be 1, 1, 2, 4, 3, 9. And then we have another function, g, that takes S to T, which is defined as follows: the sum, g of n is the sum from k to n for k minus 2 over 2. Now we need to prove that g of n is the same as f of n. So let's see here. So we have the same domain and the same codomain. G of 1 is the sum k from 1 to 1 of 4k minus 2 over 2. Okay, so k to 1 to 1, that means I replace k with 1 and see what's going to give me. So this is 4 minus 2 is 2, 2 over 2 is 1. So I have this order pair for g, 1, 1. How about g of 2? Well, it's the sum k from 1 to 2 of 4k minus 2 over 2. We replace k with 1, we already know it's equal to 1, plus we replace k with 2 because it's summation, I have to keep adding them. So here is k, replace it with 2, and we get 8 minus 2, which is 6. 6 over 2 is 3, and the answer is 4. So I have this order pair. When S2, I get the element from T, which is 4. And the same with the G of 3, is the summation k goes from 1 to 3, 4k minus 2 over 2. So I already know k of 1 plus k of 2. So when k1 and k2, if I add them, so I get 1 plus 4, 3, plus when k is 3, 4 times 3 is 12, 12 minus 2 is 10, 10 over 2 is 5. So if I add all of them, I get 9. So I have this ordered pair, which is 3, 9. So as we see here, F, it has disordered pairs, which is equal to G's ordered pair, and therefore F and G are the same. So remember here, not all function associations can be described by an equation. Technically, the equation only describes a way to compute associated values. So sometimes you could do some statistics and collect data and graph it. And here is the function or the association here. So here we have degrees, so different degrees, and here we have salaries. So as we see, there is no typical equation that takes elements from the domain to the codomain.